In this lesson, we're going to look at position time graphs. These are also called displacement time graphs, and we'll look at some very basic examples. But before we start, we're going to answer the question, what does the slope represent on a position time graph, which is a common physics question to our students. First of all, before we talk about this, I just want to remind you that position is also called displacement. It can be called either one, and that's represented by the variable x. So here in this video, when I'm talking about x, I'm not talking about the x-axis, but I'm talking about the variable for displacement x. And then time, in this case, we're going to have the variable t to represent time. And then a little bit of math reminder, slope was nothing more than the rise over run, and the rise was nothing more than the going up, and the run was going forward. And then, so here's our equation, slope equals rise over run, and let me connect it to physics. Position or displacement is change in x, and run is also change in time. So let's plug that into the equation, and we get change in x over change in t, and this should look pretty familiar to you because v equals change in x over change in t. So therefore, you make the connections, and since they're both slope and velocity equals the same thing, slope is equal to velocity. So this is one way to remember. If you see a position time graph, position is x, time is t, x over t is nothing more than the velocity. Okay, so the question that students have, they ask me, Mr. Holden, which one has the greatest velocity? And you have 3 lines here. And so, well, I want to remind you, velocity is a vector. So direction is important. So if you're going up versus going down, for a vector, for velocity, it's going to make a difference. And we'll say the positive, the greatest velocity are going to be the most positive. And the least velocities would actually go into the negative area. So a negative slope the greatest negative slope would actually have the least velocity if I was comparing. So let's take a look at this, and hopefully by now you figured it out. Since the direction matters, I'm looking for a positive slope, and the greatest positive slope here is that one right there. Now, if I was going to put these in order, this would have the greatest positive slope. This is the next greatest positive, and then this one's negative, so this is definitely going to be last. Whereas speed, if you're asked, here's a new question, Mr. Holden, what's the greatest speed? So you're trying to look at greatest speed. Well, speed is a scalar. And for scalars, direction doesn't matter. It just includes the number and the unit. Well, I don't care about the direction, if it's down or up. I just want the steepest one. And whichever one's steepest, and if you take a look, which one's steepest, and it's going to be this guy right here. So this would have the greatest speed. And if I was going to put these in order, this would be number 1. This now will be number 2, and this now would be number 3. So for speed, that'd be the order from greatest to least. Okay, so now if you ask the question, what's the distance traveled during the first 18 seconds? Here's another question students have a little bit of difficulty answering. Well, remember, distance is a scalar, and you add up scalars. You can't go backwards when it comes down. You can't go negative distance. So if I went over the course of 18 seconds, I find my time frame. In 18 seconds, I went from 0 to 40. That ends up being 40 meters. And then by 18 seconds, I'm right here. Well, I rested for a little bit. I was a little tired. And then I came back and I went 30 meters. So now, what was the total distance? Well, I add up. I went 40, then I went 0, which doesn't count because I didn't do anything. And then I went 30, so it's 40 plus 30 equals 70 meters. Okay, for displacement though, it doesn't matter what all I did. It doesn't matter that I did all this. I just wasted my time. All that matters is where am I at 18 seconds. And where did I start from the beginning? And I started at 0 and I got to 10. So really what I did this entire period is I just walked forward. So the end result, what I could have done instead of all this other stuff is I could have went forward 10 meters. So all you're doing is from start to finish, I went 10 meters forward. I am not giving a direction. If this was north, then I'd be going north, 10 meters north. But I wasn't giving a direction here. Okay, so what's the instantaneous velocity at 18 seconds versus average velocity? This is a question a lot of students miss, so make sure you pay attention. 18 seconds. So I'm looking and I find 18 seconds and I find this little point. What is the velocity right at that second? Not what was the velocity the whole time, but what is the velocity right at that second? And hopefully you remember from math, it's impossible to take the slope of a single point. So what you have to do is take two comparable points, and the easiest two are usually going to be the beginning and end points of that slope, wherever the same slope of that little point right here. And so if I'm trying to find the instantaneous velocity at 18 seconds, I can go ahead and I end off at, so I'm going to go ahead and solve for velocity. Velocity is change in x over change in t, and change in x is nothing more than x final minus x initial, and change in t is t final minus t initial. And if I look at this graph, my x final was -10. I got to -10, and I started off at 40, but the equation says minus that number, so it's minus a positive 40. So it's still -40. And my final time was 20. So at the very end of this, right here, I was at 20 seconds. And right here, I was at 15 seconds, so minus 15. So this ends up being -50 over 5, and that answer is -10 meters per second. So my instantaneous velocity right here is the slope of this line, not the entire time frame. Whereas if I was trying to solve for average velocity, this would be done different. For average velocity, I'm just concerned with where I started and where I left off. And so if I was trying to solve for average velocity, well, my change in x over change in time, my change in x was, I just went 10 meters forward. And the time it took was 18 seconds. Type that into the calculator, I get, 10 divided by 18 meters per second, and that would be my answer. Okay, and then next, displacement. Okay, displacement on a position time graph is a gift. Its displacement is unit meters. You just look at it. 5 seconds, I was at, take it up, go over, 40 meters. At 16 seconds, so it's right here, it was 30 meters. I'll just read it off the graph. So if you have a velocity time graph, you can tell two things, velocity and time. In a position time graph, you can tell two things, displacement and time. Other than that, you'd solve for it. Okay, so what's the velocity during the AB interval? AB interval, you ended off at 40. So we ended off at 40 right here. You started at 0, and your time, you finished off at 5 seconds, and you started at 0 seconds. So my velocity is going to be 8 meters per second. In this case, it'd be forward. Okay, BC even interval. Some people would realize it's a straight line. You went from 40 meters to 40 meters. You didn't do anything. But if you did the math, it's 40 meters minus 40 meters over 15 seconds minus 5 seconds, or 0 meters per second. So you are at rest. Okay, CD interval, we already solved that earlier, so I'm just going to go quickly through that. It ends up being -10 meters per second. Okay, so just a summary of what these things look like. So anything at rest is going to be on a position time graph. Once again, if you don't know what graph you're looking at, this line means nothing to you. But on a position time graph, this would be rest at 5 meters. Ignore that it kind of slopes. It should be a flat line, horizontal. 3, this would be someone not moving from 3 meters. So you can think of them person, okay, here's my number line. 0, 1, 2, 3, 4, 5. The first person up here is standing there right here doing nothing. He's just sitting doing nothing. This person would be sitting at 3 doing nothing. Okay, constant forward motion. Constant forward motion, you're going to be moving from one position to another position, but you're going to be doing that at a constant rate. So there's an example of constant forward motion. Here's another example of constant forward motion, just a little slower. Here's an example of constant forward motion. This is a little faster. Once again, they could have started off at 3 meters, that just a mark on the ground, and went, as long as it's a straight slope line going upwards, it's going to be forward motion, and it's going to be constant. Constant backward motion, it's going to be kind of like the last one, except we're going to be sloping downwards. Sloping downwards, so this would be faster, but downwards. Constantly. And then accelerated motion. Well, in accelerated motion, we're not going to go at a constant rate. We're going to go forward, but we're going to go ahead and go faster and faster and faster. We're covering more ground per second. So that's going to be a curved line. The object that was accelerating even greater would have even a greater curve up. Deceleration. So deceleration can look a couple different ways, but one of the common ways is if I was moving at a velocity and all of a sudden I'm covering less distance per second, that's deceleration. That's a possible deceleration graph.